I'll be focusing mostly on simulation, EMT simulation, and a bit down this path. So yeah, so I'll present first the current status of offshore wind in relation to grid compliance, and it goes a bit to what Han also presented. Then I'll go a bit on faults and power systems. Maybe there is someone that doesn't know what they are, so maybe one slide or two of those. And then also validation of models during operation, and finally, a bit of a different thing that I've been working on, these machine learning models. So yeah, this is like a snapshot of what the current products look like for offshore wind. And then the latest one from Siemens Gamesa is this 14 mega turbine, but there are others as well, that other manufacturers that have different sizes and so on. This slide here is a bit older. It's from 2023. It has changed a bit, the sizes of the turbines, but I think these are the four biggest players in the market. So General Electric, Siemens Gamesa, Vestas, and Mingyang from China. And then this slide is nice because it just shows the size compared to other types of objects in the world. So this is like the Statue of Liberty here. This is like a Boeing 747. This is like the Eiffel Tower. And these are like the turbines, the sizes of the turbines compared to these objects. So these turbines are getting bigger and bigger, basically. Mainly, basically, growing to reduce the costs and drive this LCOE down, create economies of scale. So the bigger turbines, less cables you need for the same amount of power, and less foundations you need. So somehow drives the price down when you have larger sizes. And at the same time, basically, these turbines soon are surpassing 20 mega of power generation. I think there is one recently from Mingyang that has been announced that is 20 mega of rated power. And I mean, this is just showing that this increasing of penetration of wind in the industry. And I guess this slide here is more on the modeling side. In the past, we had this very synchronous-based generation, and validation of models is not something new. It has been done in the past, but mostly for RMS models, so phasor domain models, RMS, root mean squared, which are basically models that I mean represent very well synchronous generators for a wide range of applications and frequencies. But yeah, this is not something that we are that is true nowadays. I mean, basically, we see that we are moving from this more synchronous generator-based solutions to inverter-based solutions. And then here we see that RMS models are not able to represent well the response of synchronous generators. So there are fast control interactions, and the RMS models are not able to basically grasp them. And this is just a slide on the current scenario of grid compliance. I think Han focused a bit more on the operational side here, which it's a very important part. But basically, we have challenges on the whole chain of grid compliance design for wind turbines and wind power plants. Going from the design here, where you have extensive verification, and then when you go, and then you have more requirements, and then we deliver these models to the developers, and then you have challenges there as well on the at plant level with basically different grid conditions, and often they also have nearby equipment in the plant that basically can be problematic. And then finally, you have an operation. You have a lot of problems that you could have, where software updates for extra features are always changing. You have grid conditions that change all the time, harder repairs, and so on. So there's challenges in the whole chain of design and operation of wind power plants. And there are also pushes from the market that things should be coming faster. You should be faster to market. You should be more reliable. You should be delivering things in an earlier time stage of the planning and designing of new wind power plants. So there's a lot of basically things that are driving a lot of different innovation required in this whole chain here. I mean, as I said, it will be focusing a lot on faults today. And I mean, most of you guys know what faults is. Maybe online, there's maybe someone that is not so aware. But yeah, you can have many faults in a power system. Cables, overhead lines, equipment. There's many different things that can happen in the power system. And I mean, you see here that we have the wind turbine. And then Agrippina showed basically the whole chain of connecting a wind turbine to substations, and you have an export cable connecting to shore, and you have a transmission system, distribution system, and then loads, which are basically our households. And then imagine that's a fault that happened here. This is not a fault in the offshore wind farm, neither it's just close by, but as a wind farm, as a very, let's say, important generation in the system, this wind farm needs to sustain, to remain connected during the fault. And this is what we call fault right through, which is basically required by grid codes, let's say, specific requirements from different countries on how you should respond and how you should basically behave yourself during a fault. And this is just an example here of a three-phase voltages. When a fault happens, the voltage will drop, and then basically the turbine will identify a fault. You will ride through the fault, and then this is basically just a very simple FRT curve from a grid code on how you should basically be connected. So within this gray zone, you should be connected. That's basically what grid code says, and each grid code tells you that you should do it in a different way. And that's basically the big challenge, right? Because you need to, as a manufacturer on a wind power plant point of view, you need to fulfill different requirements on how you ride through faults and how you should behave during faults. And I mean, one may ask, how do you simulate faults what kind of different tools you have? And then here you have different levels of complexity in tools. You have short circuit calculation tools, which are basically the most basic tools that you can have. And here, basically like static tools, they're not on the time domain. The principles of which they use are somewhat very similar to RMS simulations in a way. I mean, they use phasor domain. In a few of these tools, they use phasor domain, but they use it in a static way. They're not really calculating that for every single time step. Then you have RMS simulations, which usually use some sort of a reduced order control representation of the wind turbine, or also other types of, generation like solar and battery storage. You usually don't use the full order control here, so you use a reduced, let's say, interpretation of the actual control. And here you have also other types of tools. And finally, you have the EMT tools. I just put two here, but you also have other types as well, where usually you use full order control, basically. So you use the actual control that is on the wind turbine is the same control that is on the tool, which is what I'm going to be focusing on today. So I'll be focusing on the EMT simulations here. Ramon and I, we were going to show as well this part for you guys, but he will show tomorrow. So how do we actually use short circuit calculation tools as well for different purposes? This is more for system level planning, design, and so on. This is more for grid compliance and stability point of view. So yeah, how do we develop these models for our new wind turbine? Because I think it's very important that we understand the whole chain, right? So we go from the whole development of these models up until when we can actually use these models for actual operation. It's looking a bit different here than here, but I don't know why. Actually seeing that maybe it's missing a few colors, but it's I mean, you guys can see there, maybe it's a bit different than can you see there? It's a bit different. I don't know why, but yeah, I guess you can see the idea, right? Basically, it's a bit difficult to see the separation here, but yeah, I mean, as I said, we developed the full order control, in MATLAB Simulink, and then this gets also put into the actual turbine prototype software, and we also use that in EMT models. And we also have different other variants of models that we can basically use for validation. Here it's a nice idea of how we actually do these tests. I'm focusing only on EMT models in this presentation, so all of these other models here that I was presenting, the RMS models and so on, we basically don't focus on this presentation. So it's mostly on electromagnetic transient models. And basically, how do we validate these models? It's more or less like this. So we have the actual prototype turbine, field turbine there on site. We have this medium voltage measurement FRT test container, which is like a testing unit where you can apply different faults from the point of view of the turbine. And we also have this control center where people from the team I am at, they sit and they basically do all the tests. And we basically can obtain different topologies of faults, changing these impedances here. You can apply two-phase, three-phase faults, and basically you can, from the point of view of the turbine, it's a fault that the turbine should ride through. This is a very established way of applying faults and validating and certifying turbines for faults. And this is what I'll show one slide or two here. For the whole thing that you're going to see, for the next, I don't know, 1 hour. It's going to be all based on these models that have been validated during design. So basically, the model is on the site. We basically apply a bunch of different faults, different grid codes, and so on, and then we measure these voltages and basically play them back on the EMT cell software. So that's a very common practice. It's called playback. So the voltage that we measure on the site, we use basically a controllable DC source here, and we play that voltage measurement for the PSCAD model to respond, and then we compare the results, the currents and powers between the model and the measurement. So it's called also open loop validation. So it's like you don't have a feedback loop. This is a stiff voltage source, so there's no like so you can see that there is a stiff voltage source there. The DC voltage source is playing back the measurement that you have, but it's the best for validating a chunk of the model. And then the model contains different things, right? I mean, it contains one mechanical system, the electrical system, and finally the control system, which is a one-to-one representation. I think this serves a little bit the research for many people here. Say they say the so-called DLL approach for black box model validation, model representation from manufacturers. This is something that is very common nowadays for all the manufacturers of HVDC, solar PV, wind. All of them have some sort of a model like this where the actual source code goes into the model, and then basically the EMT model has a one-to-one control algorithm that basically represents the actual source code. And this is just 3 faults validated here. Basically, 3-phase fault on the left side, and then a 3-phase fault with fault impedance on the middle, and then a 2-phase fault, solid fault on the right-hand side here. And I mean, we do this for hundreds and hundreds of faults, right? And then of them are supposed to follow a specific grid code, either from the UK, from the United States, different parts of the United States, from Belgium, Netherlands, France. All of them are basically done for specific grid codes. And the way that the turbine responds to these faults, although sometimes it's the same fault, it may differ from country to country. So how the country specifies how much current you should inject, how fast, what should be basically the behavior after you clear the fault. So here is when the fault gets cleared, for example, and then the power is ramped up. Basically, by the way, you're seeing positive sequence voltage and negative sequence voltage here, positive sequence reactive current, reactive power, and positive sequence active power. So you see that the way that the power ramps up after the fault, this is also specified by the grid code. There are many specifications done. For example, how much reactive power you should inject during the fault. This is also specified by grid codes. I mean, it's endless the amount of things that it's specified. And then the wind turbine needs to fulfill all of this for all different grid codes. So there's many tests that needs to be done. But I mean, this here is more established in the industry. But what's not established yet, which is basically the newer part, is how do we validate during operation, which goes a bit in line with what Han was presenting. How do we basically have these faults on the system, and then basically how do we use this information, this data to validate the models. And then here, what I separated to present today is the work we have done it's still submitted to power delivery for validating 2 different offshore wind power plants on I cannot say the country, but 2 different wind power plants, 500 megawatts plus of installed capacity in each of them. By the way, this is where there should be a separation here for the second power plant. But the first wind power plant here is on the top. And then basically you can see that this area here is the part which is validated on the EMT model. And then for the lower one, which is another wind power plant, we validated the whole chunk. So the idea was to do different variations of modeling here to see, for example, what kind of problems do we see on validating a larger chunk where, for example, you may have transformers with tap changers and you may not necessarily know what kind of tap the transformer is using. This is very common. I mean, there's many things that you need to track to do validation, right? On a large system like this. So there is, for example, the tap, like I said, the operating status of all the wind turbines. You need to know all of them. You need to know how much power they were producing, if they were connected or not. You need to know, for example, the operating status of other devices here, like reactors and filters and so on. You need to know as well, you may sometimes have interconnection between two parts. You need to know if that interconnection is open or closed. So there are many things that you need to know and validate large systems like this. And what I'll show now in the next slides is that how basically can we do that? How can we validate and what kind of things that you need to have in your mind? And yeah. So the first fault that we used was keep in mind that there are 2 faults that I'll present for wind power plant 1 and 1 fault for wind power plant 2. So the first fault that we have is a 3-phase fault, 2-phase fault, sorry, on nearby the grid. It's not in the wind power plant, it's just nearby. And these are just the measurements of voltage, reactive power, and active power during the time of the fault. And this is the response of the plant model for the fault. And in this case, the validation was relatively simple because the whole plant, all the turbines were connected at the time of the fault, and the whole plant was, all the turbines were producing 1 PU of power. So they are producing full rated power. This is not so common in a large wind power plant because usually you have a large geographical area. So the wind is probably not blowing the same in the whole, let's say 40 kilometers squared or something like this. But in this case, we were very lucky, and for this reason, it was relatively, let's say, simple to validate this model because we could just basically use 1 PU for the model, and then that was it basically. There are some minor deviations here. Could point them. Yeah, here, for example, that they probably happen because of nonlinearities on the model, that nonlinearities on the system that we cannot model. So for example, transformer saturation and so on. Those are usually a bit more difficult to model. Fault B was a bit more complicated. This one here was on the same plant, but in this situation, there were turbines that were disconnected. So and all the turbines were producing different powers. So in this case, what do we know? What do we do when when such a situation happens, because we are using an aggregated model. So we are not modeling every single turbine in detail because it's too computationally expensive, but we still want to see what kind of techniques can we use to do that. So going one by one, first thing we did is that what if we assume that the whole plant is producing the power of a specific wind turbine? And in this case, it was a turbine that was producing around 90%. This is not a good assumption because the plant was not producing that, but we just try to see what happens, right? And you can see that there is a large mismatch because basically the whole plant was not producing that, but then we just forced the model to behave as if it was producing, and then we see that on the turbine level comparison, we can see that the active power matches relatively well, not so well, but it's relatively well. The voltage as well, but the reactive power completely off because the plant was not producing that power as a collective plant. So when we force that to happen, basically the plant will require more reactive power injection to keep the same voltage. Yeah, basically this was one of the cases. Then what we did is, what if we now calculate the whole active power production of the plant, and then we just put that through the model. The problem is that here, what we did is that we didn't consider the plants, the turbines that were disconnected prior to the fault. So we just said, all the turbines that are on the model, let's just divide the whole power production by all these turbines and check the model. You can see that now there is a better match of reactive power, but basically the problem now is that the ramp up of active power is not matching anymore, because when you have more turbines, you can ramp up better, faster active power than when you don't have as many turbines. This was also something that we understood that is required. So we need to account for the turbines that were not connected, find a way of removing them from the model, and also account for the total plant production. So finally, we reached the final one, which is the best comparison, which is when we have two turbines disconnected. So we remove them from the model, and we also basically average the whole plant production on the model. So this was basically considered the best match. Now we see that the reactive power is within the tolerance. We're slightly off, but still within the tolerance. And we see that the reactive power, especially on the ramp up, matches pretty well. So basically we use this model for something else. So just keep in mind that this has been validated as well for operation. So as I said, the best match is when we consider total plant production and remove the turbines from the model. So this is more or less basically the recommendation for this type of faults. When the turbines are producing a wide variation of powers, and some of them are disconnected, you need to account for everything on the model. So you cannot just plug and play. And finally, what we have here is now a two-phase fault on the other wind power plant. And then here you have to remember that we validated a large chunk of the plant. There's two DY transformers that have also tap changers. And as I said, we don't really know what the value of the tap changer. This is not something that it gets included in all the let's say, measurements and recordings. So this is something that is also a bit tricky. But in this case, two turbines were also disconnected during the fault due to problems and then to mechanical failure. And here what we found is that since these two turbines were producing very little power, we could not account for them in the model, which made our life easier. If they were producing a lot of power and then they got disconnected, for sure we would see a mismatch in the model, simply because you're gonna have a loss, a very big dip in the power when you lose these two wind power plants, these wind turbines, sorry. But yeah, I mean, there's so many learnings here. We put all of them in the paper. but yeah, I'll just go through quick all of them. Basically, we did some playback assessment, and we found that it's better to do playback than try to model the whole system. So we just isolate for the part that we need, and then we play back the model there. A lot of people can basically argue that since you have so many turbines in so many different operating points, you should have a full order model. But a model with aggregated turbines already takes 1 hour to run, more or less. If you have all the turbines there, it's going to take you good 6 hours to run for one case. So the idea is that to reduce also the computational expensiveness of the model, which is why we use aggregated. There is a very big importance of tracking software versions and parameters. This is also something important. There's many people that talk about tolerance definitions and so on. We think that it's still, I think it's still important to have tolerances when you're showcasing these results, but still there's a lot of engineering judgment as well here. One thing that is very tricky is to know the operating status of devices, of passive and active devices. I think this is one of the biggest problems in power systems now, is to actually know what all the other devices are doing when you are doing your stuff. So, I mean, here's is something that many people deal with in their let's say work in different levels, but I think this is still true here. I mean, we simply don't know to a large extent how all of these devices are operating, if which kind of control mode they're operating, if they're, let's say, doing something funny that we don't know, like, I don't know, control, automatic adjustment of control and so on, control parameters. There's all this kind of stuff that we simply don't know. So we try to specify as much as possible, but there is still many unknowns. And then that's also something that we see here. I mean, even passive devices sometimes, when you're trying to replicate a fault like this, is difficult to locate, you know, what kind of, let's say, status they were at that moment. If they were open, closed, how we kind of, what kind of status they were, if they were disconnected fully, or if they were, I mean, if they were partially disconnected. So there's many different things here. And there's also one more super big unknown, which is the nonlinearities of the system that we cannot model simply. I mean, there's simply many things that you cannot model. Simple as that, which basically, even if you have the most detailed model of a transformer, for example, high frequency model of a transformer, you still have things that you cannot model. And now if you couple that together with all the equipment and put that in a model, then the nonlinearities and assumptions, they just pile up. But still, we can still validate, but we still have to know and always go back to the engineering judgment. So you look, and you also have to do an engineering judgment on the result and assess if what you see makes sense to the assumptions, usual assumptions that you have on EMT models. Finally, one thing that is important is the selection of events for model validation. And as I said, the operating condition of the turbines at the time of the fault. So you need to know if the turbines are connected or not. If they have been disconnected during the fault is also very important to know. So there's many things that we learned and we put somehow in this paper here, all this information, these discussions that we had. I just try to go briefly through it. But in this work, I mean, the work that we have been doing, which hopefully maybe will continue someone else, is with all these learnings, we also found that EMT simulation in general is very good, very accurate, but can be limited, right? Or in the case of a large fleet of turbines. So, I mean, here we have, I mean, as a wind power plant, wind turbine manufacturer, there's thousands of turbines from us across in different parts of the world, in North America. I'm now talking about offshore. North America and Europe are basically the two markets, but onshore it's everywhere, right? So you have thousands of turbines. And you have all of these turbines, they are riding through faults. The same faults that I said, they are riding through faults on a daily basis. So we have these reports we have a tool that identifies when a turbine rides through a fault, but going from there to basically validating and checking if the response was good or not, a whole other game. So we have each of these turbines are fulfilling different requirements. Each basically turbine is doing one thing at different locations of the world. And one thing that I didn't mention is that one EMT, we cannot validate single turbines simply because of there's limitations with the EMT tool itself on replicating at certain measurement points. But what's important is if we use a wind power plant model for each of these plants, it's probably going to take us months, years to validate all the plants. Simply because there's too much preparation that you need to do on these EMT models to receive this data that I was describing here. It took me a few months to do those 3 results up there. And also because they are very expensive and very difficult to incorporate into the IT infrastructure. So, I mean, to do all the data preparation and play back on PSCAD is relatively difficult on a large fleet. So that's where we had the idea. What if, for example, we develop a sort of EMT-based machine learning model, so a machine learning model that has been based on single machine infinite bus system of a wind turbine, and we use that instead for preliminary assessment. So, I mean, here we see a response that you saw before during design. You see that it's very flat, very easy to calculate. For example, what should be this injection based on the grid code requirements for FRT? We have requirements. They are written usually in form of equations like this. It's very easy to see. For example, I have a certain voltage drop. I should get a certain reactive power. So you can calculate quite easily here. But in actual faults, you don't have these flat responses here because the fault is very fast. It clears very fast. So basically, you cannot easily understand if the response of the turbine was compliant or not with the grid codes. You cannot visually understand, and you cannot easily calculate as well. And that's why we need EMT models. As I said, the challenge is that the steady state is not achieved during faults on operating wind turbines. Very difficult, very, very rare to achieve a steady state. And when you don't have a steady state, you cannot apply these equations here. They're still not being fulfilled. Let's put it that way. So when you have steady state, they are being fully fulfilled. But when you don't have steady state, they are not being fulfilled. So basically, the idea here is that you either need EMT models or you need something else. And this is what we try to find. We try to find something else that can be used as a preliminary tool to do assessment. And from this assessment, we can basically narrow down the specific plants that are not compliant and then use EMT models only on those, So this is the EMT models, the model that we used and the data that we generated for training the machine learning model. So the model was using a single machine infinite bus system, which is the simplest system that you can have. So it's the wind turbine using the control source code, transformer, and then you have grid impedance and then a voltage source behind that impedance. It's the simplest you can have. And then basically we did 6,000 simulations, EMT simulations. Took around 36 hours, roughly speaking, but it could be reduced if you use snapshot and other techniques to reduce the computational, let's say, expenditure. And here I think it's key. We generated, let's say, a large range of faults, and from those we randomly generated 6,000 cases to basically cover very wide range of faults. And basically we randomly picked 6,000 cases out of this very wide range. So for example, fault type 1, 2-phase, 2-phase to ground, 3-phase. So that's 4 different fault types that you can have. Fault location. So with this impedance, we can open up this impedance and apply fault in different locations here. So we apply fault from 1% to 99% of this impedance. And then X by R ratio, which is the ratio between the reactance and the resistance as well, varying a lot. The short circuit ratio varying a lot. Fault duration as well, all randomly selected. And then 6,000 of those were selected. The idea here was to basically generate enough information for the machine learning model to generalize in a relatively good way. And then the idea here was to be very well inspired by the EMT model that we use. In EMT, as I said, we do playback. So from the point of the EMT model, the EMT model will see a voltage and it will respond to this voltage. And the machine learning model does the same thing. So the machine learning model basically have as inputs time series and tabular data. So the time series are voltages, positive and negative sequence voltages. And the tabular data are, for example, all the pre-fault operating points and the grid code parameters. So let's say UK grid code parameters, the machine learning model will receive that as well. And then we have long short-term memory layers for the time series, and then dense layers for the grid code parameters and the pre-fault operating points. And then we have, let's say, 3 layers here, 3 hidden layers. And then on the output, we can also inform the loss function with the actual equations that should be fulfilled. I'm not saying that they are fulfilled, but we can come closer to them and say the response shouldn't be super off, right, at this point. So we try to at least inform them a little bit of what they should be doing. And then basically to find the best match for example, number of neurons here, and so on. We use the Bayesian optimization approach, which is it's basically just randomly assigning them and trying to find the best optimal point. It doesn't guarantee global optimization, but since it's so expensive to train this, can take 1 hour. So we just try to find something quick for like 1 or 2 days of training to find the best approach here. And technically, you could also use in this input here, you could also use real faults to improve the response, but we only use simulation faults. And here's the response. Basically, we use 75% to train and then 25% to test the model. And it can be very challenging to assess the result because, I mean, you can do mean squared error, which can tell you something, but it will not tell you about, for example, outliers in the response, because those are going to be, let's say, put together with everything else. So also we can use tolerances, for example. We can apply an absolute tolerance on the whole response, and if something is off the tolerance, like we do with models, we can flag that and say, penalize that somehow with the training, or also check if there is something that can be improved. And we obtain relatively good errors, relatively low errors. But that's simulation, right? Simulation it should be easy to get a response. But what I found is nice to use this for, and this could be used also for testing as well. I mean, for simulation against simulation, looks like a good use case, but I didn't explore much. Here you see the response of the machine learning model against the response of the simulation. On purpose, I did this here. Basically, I changed, in this case, the K factor, which is the gain that the turbine should inject reactive power. So for a certain voltage drop, the reactive power should fall, should rise to a certain value. In the EMT model, I increased it to 4, and on the machine learning model, I kept to 2, which is exactly what I wanted to see. I wanted to see the mismatch, because this is what we want to use these machine learning models for. We want to use them to see if we are being compliant, if we are following what we expect. So it's more or less finding a way of having a machine learning model that represents your expectations. for a wind turbine in the field. And you want to check if those expectations are met. And this is what we see for K factor. Same thing, for example, for another parameter that we can have, which is ramp up of active power after you clear the fault. On the simulation here, on this case, I increased it to 200% per second. And on the machine learning model, I kept to 100% per second. So we can see that on the simulation, it's 2 times faster than on the machine learning model, which is exactly, again, what I wanted to see. I want to see this mismatch. This mismatch was very good news because it represents basically that the machine learning model, when it sees these inputs, this voltage profile, plus these parameters that I give to it, it will respond as it is expected from those parameters. But if the simulation or the real turbine are not responding that way, I can flag and say, okay, there's something wrong here. And then basically I can go and say, I can go deeper on trying to debug what's wrong. Is it the parameters? Is it the turbine that is faulty and doesn't respond the way my models expected? So there are many things here. Finally, this is a response against real measurements. So this is field measurement. Field measurement is always much more complicated to deal with because, again, I don't, when you simulate a fault on the single machine infinite bus system, you don't have a way of simulating what actually happens on a power system. On a power system, we'll have a lot of switching here. You see here all these red dots or arrows. They are pointing to different switchings that happen because this is a real fault that happened on the system. So there's many devices that are gonna respond to this, many circuit breakers that are gonna open and so on. I cannot possibly model that on a single machine infinite bus system to train my machine learning model. So, but since I'm using sequence components, which somehow filters out a bunch of stuff, this also gets filtered out. And then instead, what the response I get is more or less like this. So blue is the actual site measurement and red is the machine learning model. If you would say this is perfect, this is not perfect, but the intention is not to be perfect. The intention is to do somehow a preliminary assessment on the whole fleet of turbines, which are thousands of turbines. If we were to do EMT simulation for that, we would spend years and we would still not have, let's say, all the conclusions that we can take, but instead we can use this to say, okay, this response looks relatively similar compared to the expectation. I think this model, this plant is going, let's say, on the right track. It's matching our response. It's matching our expectation. What about the other one? And then if the other one looks something like this here, then we definitely know there is something wrong with that plant, or that definitely know that we should investigate further. And then we can use the EMT models that I was showing before that have been validated. So the idea is to find ways of having preliminary assessments, making things a bit faster, because right now the idea is that, I mean, the reality there's very rarely we do something like I did before, only when something very bad happens. But if you want to perhaps bridge the gap and make things faster, we could do something like this. A lot of people get a bit offended with this type of approaches because they are, I mean, relatively not the most physical based approach that you can have because you are using, let's say, an approximation. This is nothing more than approximation, the way I see. It's like you try to find a way of approximating and make things faster, right? But still, I think that for preliminary assessment, for assessing a large fleet of turbines where you have faults happening daily on all the plants, this could be very useful. And then, yeah, I mean, it looks a bit different from here, but the colors are a bit, but yeah, basically the idea is that we have on the design here, we have these models that have been validated. And here I didn't show this part here, but there's a lot of work that we are doing on subsystem validation as well. But basically we use these models, these validated models to obtain these machine learning models. And during operation, you use them together you use machine learning models to do preliminary assessment. You use them as well to do some other types of pattern recognition on your plant. But somehow I always try to base them on EMT models. So I always try to go back to the quote unquote physics in a way to somehow keep grounded. So keep the things grounded. And we can use also these EMT models to continuously validate and perform compliance verification. And here, this part is all about the data and databases that we use. So we have to keep track of all the parameters. So there are hundreds to thousands of parameters that we need to use to parameterize these models. And we also have a large database of these events, and we need to retrieve these events, pre-process them, check if the quality is good, parameterize everything, and then perform the compliance. So this is more or less the whole chain I showed here. It's jumped a few of these steps or the explanation for them. But yeah, that's more or less the whole chain of the validation and let's say modeling strategies that we use. Yeah, conclusions from my side. I don't know how much time I took, but I hope it was 45 minutes. Yeah. So I mean, as I said, that the number of the wind power plants are growing. We need to continuously assess the stability and grid compliance. I think everyone is doing something like this here in different ways. I mean, not everyone. Some of us are doing something like this in different ways. But what I wanted to show is that we have modeling strategies that are only gaining more maturity, and we are developing more and more those for modeling faults and other events on wind turbines and wind power plants. And what we are also now trying to take a step is towards operation, because we have matured a lot on the design, but on the operation we still have a lot to mature. There are many challenges when doing that on operation, plant level and operation. There's many things that are unknown. There's many things that are uncertain. Many things that you need to dive deep into all the databases to find the information. They are not all collectively, let's say, put together by these, because there are different devices that use different databases, different ways of storing stuff, and so on. So it's very complicated sometimes to piece the whole event together. A fault happens, to piece the whole fault together and understand how all of the different things were collectively connected at the time of the fault sometimes can be very challenging. So yeah, it may take a few days to understand how that fault happened. So you need to go through here and say, okay, this turbine was disconnected, this switch gear was, this connection point here was connected, so the two export cables. So there's many things. But at the end, I mean, also a key maybe idea on this presentation is that we can have new methodologies. There is a place for them. I wouldn't say that they are substituting anything. They are only complementing. And that's basically the idea here. We don't want to really substitute EMT models, physics with machine learning, at least in very, let's say, critical operations, but we want to find ways of using this for preliminary assessments, for speeding up assessment and trying to narrow down critical cases. So that's this last work that I presented is focused on that. So when presenting this to very hardcore electrical engineers, you need to mention this many times, because people don't want anything to be replacing the physics-based tools that we have. Ideally, we want to improve and we want to make life easier. So these tools here, they can basically improve this preliminary assessment of grid compliance on a large fleet. And then with this understanding that we have, we can narrow down to the most critical cases, and then we can use the EMT models that are very heavy, very difficult to parameterize, but that's somehow something that we can do after we use other tools for narrowing down.